My name is Vanessa. I'm a senior engineer at Daily, where I work in an automated test framework for our real-time video and audio chat API. While by day I make headless WebDriver instances, join WebRTC meetings and live streams, by night I break digital files with artistic and investigative intentions. I engage in a dark art, exploiting video compression artifacts to make sophisticated visual journeys and memes. It happens to be a fantastic vehicle for learning about the AVI file format and the MPEG compressed video streams contained therein. So let's hop in and learn what's in a glitch. This is my ode to data moshing. What is data moshing? It's a subset of glitch art, an umbrella term for art and music made by intentionally corrupting digital files. It was the hot new thing in the mid-aughts, first in the art world. Takeshi Murata's Monster movie in 2005 is a prime example of the early age of the technique. In 2009, Kanye West used it in his music video, Welcome to Heartbreak, and incidentally, this is when the aesthetic first appeared on my radar. Between me and Kanye, data moshing is mainstream, and the internet has steadily used it for meme purposes since its inception. Speaking of, these memes here show off one of the two main flavors of the aesthetic, removing iframes. This is commonly combined with repeating p-frames. And this second technique is a particular favorite in pizza eating GIFs. Seriously, I think p-frame should unofficially stand for pizza frame. And with that segue, let's dive into what IMP actually stand for and how the motion picture experts group compresses video into these frame types. To compress data, video or otherwise, means we want to make it smaller. To do this, we want to identify and make parts of the data repeat as much as possible, because storing the info 200 times Space Invader is smaller than 200 Space Invaders. Take this short video. Let's break it into frames, both I and P. We make the first and last frames iframes, also known as keyframes. These are intra-frames, that's where the I comes from, meaning we only look for repeated values within the same frame to compress. This is accomplished by carving up the frame into 16 by 16 pixel groups called macro blocks and applying JPEG compression to each. And as much as I would love to explain JPEG compression in depth, we don't have that kind of time. But here are the highlights, which help explain the artifacts seen in glitch art. So for each macro block, we convert to YUV color space, which is our first win. The human eye notices differences in luminosity more than chromaticity, so we don't notice the loss of those color values. And then, this is the biggie, we apply the discrete cosine transform, aka DCT. And this is just fancy math that involves this table here. It basically asks, what if this wasn't a macro block of pixel values? What if it was a frequency made by multiplying only these 64 cosine functions? The answer to that question turns all the macro block values into frequency coefficients, which, just trust me on this, tells us we should keep the lower frequency values. We then make the higher frequencies 0. And now we have a lot of repeated values, just like the Space Invaders. And here's big win number 2. The human eye notices changes in low frequencies more than high frequencies, so we don't notice the loss of these values either. Finally, we make like an overzealous Zorro and we line up the zeros so they can be compressed. And now you know 4.5 of the 17 steps of JPEG compression and why this is FFmpeg's logo. The other frames are p-frames, also known as delta frames. They are predictive frames, and along with bidirectional frames are inter-frames, because we take advantage of temporally as well as spatially repeated data. The beginning of this compression process is the same. We carve up the frame into macro blocks. And then each macro block can contain one or more of the following. Motion vectors. It says take the pixel value from this macro block and move it. This is best illustrated by FFmpeg CLI's export motion vectors debug filter. Here we can see arrows in each macro block representing the direction and magnitude of the motion vector. Difference DCT coefficients. This is more fancy math based on the other fancy maths. We just keep the differences between the frequencies of the previous macro block and the current one. And 3, sometimes neither of those is possible, so we fall back to just plain old JPEG compression. If this is all clear as mud, great! The key takeaways are these. Don't sweat the details and make data repeat. It's okay because the human eye notices differences in low frequencies, like a soccer ball in a field, more than high frequencies, every blade of grass in said field. There are iframes, which are essentially standalone JPEG compressed images, and there are p-frames that use motion vectors and fancy math called DCT to rely on other frames to render a full image. Film strips have reels, composite video signals have VHS tapes, and laserdiscs. We need to hold a video stream in a container. There are lots of container file formats, QuickTime, MP4, Matroska, and they can all hold MPEG video streams. But datamoshing loves AVI, the audio-video interleave file format. But if datamoshing manipulates the compressed video stream directly, why does the container matter? Why is this file format so popular? Well, first, it was around. Microsoft introduced the format in 1992. Also, it's simple. It uses a type-length valued chunk structure because it is a subformat of RIFF, which is based on if, which also spawned AIF. Oof, there it is. The most interesting part of the AVI file is a list chunk named MOVI, which contains the actual frame data. Conveniently, each frame of a compressed video stream is also a chunk and begins with a 2-digit stream number followed by a 2-character code that defines the type. Here, DC indicates compressed video. There's also an index chunk where the entry includes metadata about the frame. For example, is it an intra or a predictive frame? My favorite part, though, is there also exists a junk type chunk where the data is simply ignored. Sounds ripe for steganography. Just saying. This junk chunk is also indicative of why AVI is so popular for datamoshing. It's a bit of a YOLO file format. When I say I remove an iframe, I don't actually remove the data from the movie list and recalculate the length of the list and update the chunk length. I simply fill the particular iframe chunk with garbage bytes, and AVI just doesn't play that frame because it says timecode schmimecode. I mean, not really, but for our purposes it does. On to a simple example. I removed all iframes from the second clip and let the following p-frames go on their merry way as they unknowingly use incorrect reference data in their motion vectors and difference DCTs. Voila, moshed. And here is a slowed down snippet with the macro blocks and outlined and the motion vector arrows. To make this and the following examples, my mosh process started by rendering uncompressed YUV QuickTime clips from After Effects. These were encoded to MPEG-4 in the AVI format via FFmpeg. For the actual moshing part, I used an NPM module, AVI glitch, to write some basic code to destroy all iframes except for the first and repeat the last p frame a lot. It should be noted that the frames we are watching have been baked. It's great to make a busted moshed AVI file, but realistically, you gotta re-encode it proper and put it in a more current and accessible format. So again, I used FFmpeg to make an MP4. Now on to a slightly more complex example. Here are 8 clips moshed. It basically results in the coolest Trapper Keeper pattern on the planet after repeating the last p frame into oblivion. I was pretty pleased with how it turned out. But then I got curious, and I applied the same process to MPEG 1 and 2. There are minor differences, most apparent in the final p frame oblivion. MPEG 4 is less blocky, but they're all in the same ballpark. And that's when I got a little more adventurous, and I tried mixing and matching MPEG versions within the same moshed video, with admittedly varying degrees of success. But that's when the DCT table started showing up again. It seems the fancy maths and macro blocks didn't always line up between the different MPEG versions' p-frames. So instead of being set to 0, some higher frequencies snuck through to the final result. And after applying the export motion vectors filter to this MPEG medley, I found it became quite painterly. While there are no rules in datamoshing, I can offer some observations and guidelines for success. Keep all clips the same size and aspect ratio. Motion vectors seem to shine when all footage is the same codec. The DCT artifacts are more apparent with mixed codecs. It's also more volatile and might not work depending on the order and combination. And finally, H.264 is a great baking codec, but not so much for the moshing part. Speaking of baking, in my experiments, there was a file that was a little too corrupted and FFmpeg refused to re-encode. So in an effort to capture this really mosh video to share with you, I resorted to screen recording the VLC media player via QuickTime and then re-imported the video into After Effects. These steps, however, unintentionally mosh the video even more, which this is my thesis, man. This is my closing argument. It's no glitch. Data moshing is fun. Thank you.